Question number 86 asks for the magnitude of the resultant electric field at the center of this circle. However, the charges are directly opposite from each other, so the electric fields produced by each charge would cancel the other one out. So the resultant electric field at the center of the circle would just be 0. Question number 87 asks for the amount of work that would be required to bring a seventh particle of charge Q from very far away and place it at the center of the circle. So for this question, we're going to use the equation W is equal to Q times V electric potential. So V is equal to E, the electric field, times D, distance, or in this case, we're going to use R. So we just put this back into the equation because we get W work is equal to Q times E times R. To find E, we don't use the same concept we use in 86, question number 86, where the electric fields cancel each other out. Instead, we just add them together. So we get E is equal to 6 times KQ over R squared. And K is equal to 1 over 4 pi epsilon. So if we put this back into this equation, we get E is equal to 6 times 1 over 4 pi epsilon times Q over R squared, which is equal to 3Q over 2 pi epsilon times R squared. So we plug what we got for E back into this equation for W, and we get W is equal to 3Q over 2 pi epsilon times R squared times Q times R. So this cancels each other out, and this becomes Q squared. So the answer is 3Q squared over 2 pi epsilon times R, which is answer choice D. Question number 88 asks for the vector that best describes the direction of the electric field at point A, which is this point. So to do this question, we just draw a line from point A to where the equipotential lines are the most condensed. So it looks somewhat like this. However, we need to take into account the fact that the magnitude of the slope of the electric field is dE, which is dE is equal to the change in electric potential over change in distance, or R. Oh, is equal to the negative change in electric potential over the change in distance, R. So it would basically just be the negative of this line, so you just need to reflect it over the y-axis, and it will look like something like this. So the answer to this question is, question number 88 is A. The point at which, question number 89 asks for the point at which the electric field has the greatest magnitude, and the point where it has the greatest magnitude occurs where the equipotential lines are the closest together, because there's a greater change in electric potential over a smaller amount of in a shorter distance. So the answer to this question is B. Question number 90 asks for the net work that must be done by an external force to move a -1 microcoulomb point charge from rest at point C to point E. So for this question, we're going to basically use the same equation in 87, except we're going to change it a bit. We're going to use delta W is equal to Q times delta V. So delta V is equal to the electric potential at point E minus the electric potential at point C, which is 10, and it's equal to 10 V. So we put this back in the equation. Q is negative 1 times 10 to the negative 6 coulombs times 10V is equal to negative 10 microjoules. And this is answer choice B. For question number 91, we're going to find the question number 91 asks for which variable, when decreased, would increase the capacitance of this capacitor. So we're just going to use the equation for the capacitance of a capacitor, which is C is equal to K times epsilon times A over D. And since D is inversely related to C, when D is decreased, the capacitance C will increase. So the answer to this question is D. Question number 92 says, a physics problem starts, a solid sphere has charge distributed uniformly throughout. It may be correctly concluded that the only statement that's valid here is answer choice E, since metal objects or other conductors have since metal objects have charges that are located on their surfaces and not on their centers, and so the charges cannot be distributed uniformly throughout them, because then there would be charges in its center, and this does not fit into the definition of a metal. And we're going to skip question number 93. In question number 94, a negatively charged rod is brought near but doesn't touch an initially uncharged electroscope, and this is shown in part 1 of this picture. The electroscope is then touched by a finger, and the leaves collapse in part 2 of the picture, and the rod and the finger are both removed in part 3 of the picture. So basically we just need to find the charges on the leaves at part 1 of the picture and part 3 of the picture. In part 1, the negatively charged rod repels electrons to the leaves over here, and this is why it opens up, since the negatively charged things, because both leaves are negatively charged and they will repel each other. So at part 1, the leaves are negatively charged. At part 2, when the finger touches the electroscope, electrons from the electroscope are transferred to the finger. They're transferred to the finger. So in part 3, when the finger is removed, it will have a net positive charge. So that's why the answer to this question number 94 is D. It's negative in part 1 of the picture and positive in part 3 of the picture. Question number 95 asks which of the following statements could be true when a positively charged conductor attracts a second object. So statement 1 is obviously true, since a positively charged object will attract a negatively charged object, and that's just common sense. Statements number 2 and 3 are correct as well, since neutral objects or objects with zero net charge are attracted by any charged object, positive or negative. And that's why the answer to question number 95 is E, 1, 2, and 3.